for at least limestone, these pieces are just an unintentional byproduct of their use as some sort of expedient core reduction strategy. So over time, just because we see on cores, as cores become closer to exhausted, the edge angle increases. So we could end up with a sort of more rounded shape. And you can see an experiment of that there. Others argued that it's not so unintentional, that it's one long reduction sequence that was intentionally made. So from polyhedrons through subspheroids, spheroids, and eventually what some people call bowlers. This exists in one intentional reduction sequence. What they were wanting to make them for is unclear at this point. But at least the other idea is that it's intentional. So this morning we want to test these hypotheses. And so to do this, we need to look at a few different variables. So for instance, if they were used as a hammerstone or percussor, we should expect to see flakes being removed, of course, as it's hitting a hard object. But the scars that are being removed should be pretty haphazard. We shouldn't really see much structure or patterning to these scars. But as Schick and Toth and others demonstrated, we should expect to see them over time become more rounded and more spherical. And their idea being that when you are using these stone balls as hammerstones, perhaps, the more spherical part goes in your hand, and any angular bits are sort of protruding, and they're the bits that come into contact with whatever you're hitting. So over time, getting that more rounded and spherical morphology. If it's being used just as an expedient core, then we should see some sort of scar patterning, even if it's a very expedient core reduction strategy. There should be some pattern to the scars that we see. As Sanuni demonstrated, we could even expect it to become more rounded. But I would argue there shouldn't be a tendency for them to become actually spherical. And here we need to make a clear distinction between what we're saying is rounded and spherical. So rounded, I'm referring to the phenomenon where things can even naturally become, surfaces can become smoother, angular portions, corners and things can be removed. So this can happen even in a river. A stone ends up in a river over thousands of years. It becomes much smoother and much more round. But it's almost impossible and almost never happens that it'll actually become truly spherical. And when I say spherical, I mean an actual geometric mathematical sphere. You'll almost never see a river cobble that's a sphere. So an unintentional product probably, I think, shouldn't create a sphere. That's something that actually has to be intentionally imposed. So if it is an intentional reduction sequence, therefore, we should expect to see it more spherical. There shouldn't be, if they're removing flakes and facets and things, it shouldn't actually become more rounded. And we should see some sort of scar patterns, and a more formal scar pattern than if it was so this means we need to measure all these variables, so we can measure scar attributes like the surface area of the various scars, the edge angle of the scars. We need to measure things like the roundedness or smoothness of the objects, and also how spherical these objects are. And these are the sort of things that we compute at the Computational Archaeology Laboratory. This is a shameless plug for the lab. This is Lior Grossman's lab. And there we scan all sorts of artifacts and create 3D models, which are made up of hundreds of thousands of coordinates and triangles that connect those coordinates. The problem is that's hundreds of thousands of data points, which becomes a challenge to sort of analyze in any meaningful way. So in the lab, Lior and other lab members create a different software. Some software is for pottery, some is for engravings and cut marks, anything with a negative impression. Some is for geometric morphometrics with semi-landmarks. And the program we'll be using today partly is Artifact 3D. And all of these are freely available to use and download if you like. And yeah, so today we'll be using functions that are contained in Artifact 3D and also some metrics we created specifically for this project because spheroids have such sort of peculiar morphology. And just if you do want to use Artifact 3D, we recently published it and it's available online. If you can't actually see the link there, but if you email myself or Lior, we can help you get started there. But so what does Artifact 3D do? The first step is a very important one, and it takes our 3D model and it gives us an automatic orientation of our artifact. based on normal vectors, which we don't need to go into now, although we'll talk about them more in a second. But the important thing here is that it gives us an automatic orientation, which means that if I scan an artifact, put it in the program and ask the program to give me some automatic measurements, and then I give the artifact to someone here, and you go upstairs and scan it yourself, put it in the program, you'll get the exact same values, which is important because if we use calipers to do that, we would every time we measure it, we'll get a different number. So that's the sort of first step. Then we can compute a bunch of different variables. Some are quite simple, like volume and surface area. Simple metrics, but you do require a sort of 3D model to measure that, unless you want to put your spheroid in a bucket, see how much the volume changes. We can also compute the object's center of mass values. For a lot of artifacts, this has sort of technofunctional implications. So you can look at different artifacts like Acheulean picks and headsacks. The center of mass is quite low in the hand, and that allows you to sort of dexterously manipulate the tools. Whereas later sort of Neolithic bifaces have center of masses much higher on the object. And this is advantageous if you have sort of transversal actions, if you're chopping or pounding or something. For our spheroids, though, it relates more to how volumetrically or how equally the volume is distributed on these artifacts. So you can see if we put a box basically around these objects and compare the center of that box to the center of mass, any sort of protuberances and bits that are, angular bits that are sticking out will pull those two coordinates apart from each other. Whereas a very beautiful spheroid, those two coordinates will be virtually the same. We can also compute edge angle, which I'm sure everyone here has tried to physically measure edge angle with goniometers and things like that. It's notoriously difficult. So thankfully, Francesco Valletta, who was a PhD student in Lior's lab and now a postdoc there, created a function in Artifact 3D to measure edge angle in a more objective way, which is a massive relief for us. And so for our spheroids, we'll be measuring, the angle between the scars and the remainder of the surface. We can also automatically identify the scars on lithics. So using maximal principal curvature and finding the areas with maximum principal curvature, and then clustering those areas with geodesic distance, we can end up basically just putting on the scar ridges that we normally draw in lithic analysis. We can also then segment the artifact based on those ridges and compute things like its surface area and curvature and a bunch of different variables automatically. So that's what we're using Artifact 3D for. There's a few other functions in the program, but they're not useful for our spheroids today. But we also needed to come up with a few other things to measure these spheroids. And so just specifically for this project, we looked at surface curvature as a measure of sort of, you can call it surface roughness or smoothness or roundedness. And the idea here is that we take the normal vectors, which we mentioned before, and these are essentially just imagine a perpendicular line coming out from the 3D model from the mesh. And the idea here is that for a sphere, if you zoom in really, really close on a sphere, the surface is essentially flat, just like where we know the Earth is round, but our perception of it is that it's flat because we're very zoomed in on the surface. So for a very, very smooth and round spheroid, the normal vectors should all point in the same direction, and we can measure how differently they point. Whereas any curvature on the surface, the normal vectors will start pointing away from each other. And so on some example spheroids there, you can see anything like scar ridges, facets, pecking marks, cortex gets picked up as a surface curvature areas where it's not smooth or round. And you can see how it's some people would call that a bowler. It's very, very smooth on the surface. Also, importantly, we need to measure, as I mentioned before, sphericalness, which is how closely these artifacts conform to an actual mathematical sphere. And here we use spherical harmonics, which we don't need to go too much into the details of. I'm sure some of you are familiar with it, and if not, you might have heard it, might be more familiar with, say, Fourier analysis or elliptical Fourier analysis. The concepts for all these are basically the same. Essentially, you're using equations to model a real world thing, a curve, or in this case, a spheroid. And to these equations, you add sets of coefficients. The more sets of coefficients you add, the closer your object comes to sort of the real life object. So for instance, we have our friendly bunny rabbit here and our spheroid. And as we add more coefficients, we get closer to the actual object. But because on the last slide, we've already measured the sort of surface properties of these spheroids, here we're interested truly just in their geometric, volumetric properties. So we're only interested in the first 3 sets of coefficients, which tells us how much it deviates from a sphere. If we look at any further sets of coefficients, then we start sort of looking at the surface topography rather than its geometric properties. So this gives us a measure of sphericalness, a simple number. We can also visualize this with Gauss maps. You can see on the right there, where brighter colors reflect the areas on the spheroids where they deviate most from the sphere. So, for instance, this one at the top is almost cube-shaped, and each of the spaces of that cube, show up in really bright colors on Gauss maps. Whereas this piece here, which is much more spherical, but still has many facets. So most of those facets show up as deviating from a sphere, and then we get all those facets disappear eventually, and we get this very, very close to a sphere shape. And as we'll see, some of them are remarkably close to a sphere. But so what we want to do now is see if there is a reduction sequence for these spheroids. So just a brief mention of our sample. So we sampled 174 of these stone balls, and we were looking for basically the broadest sample that we could find, any globular sort of item from Ubeidiya. So anything that people have in the past called polyhedrons, subspheroids, spheroids, or bolas. And we even threw in some cores, the things that they really do look like cores, but they're pretty globular. So we included them just for variability. And then the question is, do all of these pieces belong in a spheroid reduction sequence? Only some of them? So here we'll be looking for sort of any discontinuities in this sample. Any way we can break it up if we can. Maybe we can't, but we'll see. And the idea here is that even though there's lots of hypotheses about how these were made, and no one can agree, I'm sure we could spend all day talking about them and we wouldn't agree on it probably. But the one thing that we can agree on is that the sequence has to look like that. Because lithics is a reductive process, it has to start with a bigger shape. It's not going to be a spherical. And over time, okay, it looks more like a spheroid and it gets smaller. So really, it's that last stage that we can agree upon. Even though it's hard to distinguish a subspheroid from a spheroid, there are pieces that are so spheroid-like that we would all, I think, agree, this is a spheroid. So this is sort of our starting point. The one thing that we can agree on. So we're looking for items that perhaps don't belong to this sequence. And the first thing that sort of hints that there may be some sort of way to separate the sample is that when we look at the different raw materials, they do vary a bit. Now, basalt here has a very low sample size, so we can't really do anything statistically with that. But when we compare limestone and flint, they're markedly different in terms of their surface roughness and their sphericalness. And this is great news because when offered by Yosef and Mahmoud Goranimbar originally analyzed this assemblage, they observed that everything basically that they called polyhedrons, they noticed was on flint, and everything that they called spheroids and subspheroids was on limestone. So here we have a sort of objective way of verifying their original observations. So we think that there's probably a way to separate this sample. So we'll look at some geometric ways of doing this. And again, as I mentioned, the one thing we can agree on is that last stage, spheroids that are actually spheroids. And so we went looking in our sample for the smallest of these spheroids. Now, of course, you can make a spheroid of any size. You can make a spheroid this large if you want. But we don't tend to find spheroids of that size, and at Ubeidiya that they're not, nor are they that big. The smallest ones are about 4 or 5 centimeters across. And so because our sample is relatively large, and we did try to include as much variability in the sample as we could, including the smallest pieces, the largest pieces, we're relatively confident that if we look at the smallest really spheroid-like spheroids, that's about as small as the spheroid they probably wanted to make. So then if we have something that's smaller than that item, for instance, it probably doesn't belong in that spheroid reduction sequence. But it's not just size that matters. So here you can see, because lithics is reductive, of course, things get smaller. This larger piece, when we overlay them on top of each other, we can see this one can be turned into this one, easy. Now, this piece, which is bigger by surface area than this circle, when we actually overlay them, because this piece is a bit irregular, it's not spherical or circular enough, this can't be turned into that. So we need to not just look at size, but also their shape. So we compute the maximum inscribed circle in 3 different projections. So the sort of front view, top view, and side view. And this is basically just the biggest circle that you can fit in these objects. And the idea here being that we can find cases where we want to exclude this because this can't be turned into that. And here we have an example. So the piece on the right is by volume and surface area a little bit larger than that spheroid, and that's one of our smallest spheroids that we have at the site. But you can see its circle in red compared to the circle of the spheroid in blue. It's too small. It can't be turned, I would argue, into any of the spheroids of the size that we get at Ubeidiya. So this is how we can start to sort of separate out this sample. When we remove the lowest quartile of sphericalness values and the lowest quartile of that maximum inscribed circle values, we end up with these pieces, which we'll look at some examples. Hopefully they look like cores or polyhedrons to you. We'll have a look on the next slide. We also have 4 just remarkably large pieces. It's something that, they look like spheroids, or even people might call them bowlers, but they're truly massive. It's ridiculous. So it's something different going on. So we'll separate those as well. But what we're left with then is the sample in the middle, which I would argue are spheroids. Many of these items are things we would all agree are spheroids, plus anything large enough and spherical enough to potentially be turned into a spheroid. So looking at what we've excluded from this sample. So we've excluded items like this. Now, almost all of these are on flint, as Bayosef and Namagar and Imba noticed. And here, I think, or at least I hope, none of these items look particularly like spheroids. And then here we have these just preposterously large pieces. This one is bigger than someone's head. And these are remarkably round and smooth, the smoothest and most spherical pieces we have, but they're just much, much larger than the remainder of the assemblage. So unfortunately for now, we'll throw these away, but they're still very, very interesting. And actually, I suspect the reason they're there, I have no idea. But to me, they remind me a little bit like, in the Acheulean, just at some sites, occasionally, we just get the giant hand axe for some reason. People have argued about why that is, but we don't really know. And I suspect it might be a similar phenomenon. For some reason, they just make the same tool, but just bigger, maybe. But in any case, it's not what we're really focusing on this morning. So now from our assemblage of 174 stone balls, we're left with 124. And interestingly, on those 124, almost all of them, 118, possessed what we came to call a primary surface, which was normally a large sort of remnant of a very large flake scar, probably removed very early in the sequence. Sometimes it was also cortical, like a flat surface, or a flat surface from a break, but mainly a flake scar. And they do resemble very much a sort of platform that we see on a core. And here you can see the sort of criteria we use to identify these primary surfaces on these spheroids. They're typically the largest scar on the surface. They also have a lot of high convexity. You can sort of see on these projections up there also how convex these pieces are. They also can sort of possess the most flakes being removed around its perimeter, sort of orthogonally being removed around the outside of that scar. And when we look at the spherical harmonic analysis and the Gauss map, what we identified as the primary surface was almost always the area of maximum deviation from a sphere. So an interesting pattern this year. Interestingly, also, I think the convexity of these primary surfaces probably also helps in the production of these spheroids. Because as we know, a spherical shape, the edge angle of a sphere is approaching 180 degrees, which in the process of napping, any sort of napping, is very difficult. But very importantly, that convexity of that scar reduces the edge angle a little bit when you're striking from that primary surface. So a hint maybe at how these were being made. But again, the experiments that we're conducting from today and that Deborah and the team here have already conducted sort of have also looked into that. But here you can just see some examples of these primary surfaces highlighted in black. You can hopefully see that they're quite large on the surface, very central and very convex. Again, if you look at sort of that projection, you can often see that convexity quite clearly. We'll come back to these, but I also just wanted to mention that we do see these at other sites sometimes. For instance, Stefania in her PhD work noticed a very similar phenomenon at Brancodillon, where very early in the sequence, a large flake was removed, from which around the perimeter of that was removed these orthogonal flakes that are shown in yellow there. But we see it also at Kesem and Humal, and Grenin found some spheroids at GBY, north of Bridger-Julian. And again, on these pieces, I think you can sort of identify some of these primary surfaces. So a nice hint that it's not just a phenomenon perhaps at Ubeidiya, but perhaps it's something we're seeing elsewhere as well. But coming back to Ubeidiya for now, these pieces here are ordered by the size of the primary surface, the surface area, as a proportion of the total surface area, sort of working our way down the page over here. And I hope you can see that there's sort of some trends here. So they do get a little bit smaller as the primary surface gets smaller, and the pieces get a little bit more round and a little bit, they become more spherical. We'll look at the numbers of this, but this was sort of the trend that we started to notice. When we look at these variables, we can plot, for instance, the primary surface, the surface area of that primary surface against, for instance, the edge angle between the primary surface and the remainder of the spheroid. And when we do that, we get a relatively strong relationship. So basically, as these primary surfaces get smaller, the edge angle gets higher, which of course is what we expect to see when people are napping cores. As cores get closer to exhaustion, that exact thing happens. Platforms get smaller and edge angles get higher. So a nice hint at sort of what we're seeing here. When we look, we can sort of model this geometrically and sort of to help us understand perhaps how these are being made. If we look at sort of the same relationship here, it sort of shows us that this primary surface is removed very early in the sequence, creating this sort of 90-degree angle and a very large primary surface, which is, in this, if we approximate it like a cube, it's a sixth of the total surface area, which is about what we see from our model. And then flakes are removed around the outside orthogonally from that primary surface, which reduces the surface area of the primary surface, but the angle is still 90 degrees, like we see in both of these plots. And then eventually they start removing some corners, and this starts to increase the edge angle and decrease still the primary surface area. And then even it gets closer to being spherical, and same thing happens. Higher angle, smaller surface area. And what I think we have here is this primary surface area then, if we're thinking of it just like a core, is a useful metric or a proxy metric for the reduction intensity of these tools. So I think we can sort of chart how these tools are changing throughout their reduction sequence. So using, looking at the surface area as reduction intensity, throughout the sequence, we see some interesting relationships. So for instance, they do get a little bit smaller from the biggest surface area to the smallest. It's a reduction of about a half of volume, which interestingly is very similar to the relationship in loss of volume from a cube to the largest sphere that can fit inside that cube, which is about, the relationship there is pi divided by 6, which is about 2. So here I think we sort of see on these spheroids that actually not much mass is lost in the reduction of these spheroids. And this is also supported by the fact that this primary surface is present on almost all of these pieces. Even the most spheroid-like spheroids still have a tiny, tiny remnant of this primary surface. So I think that sphere inside a cube is a bit of a model of how these are being made. very interestingly, when we look at the surface roughness or roundedness, there's almost no relationship. So as reduction proceeds, these pieces don't get smoother. They don't get sort of naturally more rounded. But also interestingly, when we look at center of mass and more precisely the spherical harmonic analysis, throughout the reduction sequence, they become markedly more spherical. And I should mention that the spherical harmonic analysis is incredibly sort of sensitive to even minute deviations from a spherical shape. So even imperceptible changes, pieces that you can't tell which one's more spherical, the computer can work it out. And you can see that these values, they approach zero, which is a perfect sphere. So many of these items, and especially the more reduced items, truly are very close to a sphere. So we'll come back to our hypotheses here. And I hope we can agree at Ubeidiya at least, the pattern that we see is similar to what we expect to see if it is an intentional reduction sequence to make these tools. For whatever reason, we don't know why they want to make them, but it seems like they do want to make them intentionally. Because we see a pattern in their scars, we don't see them become more rounded, but they do become more spherical. So at Ubeidiya, at least, we think that the spheroids were intentionally made. And not only were they intentionally making them, but that the goal of that production was to actually make a sphere, a mathematical idea of a sphere, which is remarkable to us, I think. And so to summarize all the findings that we got from this 3D analysis, the first thing we were able to do was to divide the sample into three groups. And instead of us imposing our own typology on them, we were able to, just using some simple geometry, separate them into things like polyhedrons, maybe cores. At the other end, some very weird, very interesting pieces that are very large. And in the middle, a bunch of spheroids and a bunch of pieces that probably belong to this spheroid reduction sequence. Then we have this proposed spheroid reduction sequence, which the experiments which we're continuing today and have already been done. There's a poster outside, actually, that you can see that Deborah put together about the experiments about making this. But yeah, so this is from the 3D analysis, this is what we suspect is happening. Large flake being removed, flakes being removed around the outside, corners being removed, and then more faceting removals. The question is how do they do those last two steps, especially that last step is very unclear. It's very difficult, whether it's just bashing them, bipolar percussion, passive percussion. Maybe they're very good at, they're certainly very good at removing these flakes. So how they're doing them is a little bit beyond us at this point. So we hope to be able to work that out. And then lastly, the question is, why do they want to make a sphere? We think that they actually do desire this shape, this spherical ideal, like Platonic ideal of a sphere. And so the question is, are there any any functions that necessitate a sphere, or any functions that are improved by having a sphere? And your guess is as good as ours. There's a few maybe, but it's not abundantly clear which tasks really require a sphere rather than a rock. You can find plenty of pretty round rocks. So this helps us sort of create the hypotheses for our experiments. And lastly, the fact that they're imposing this sort of shape on the stone is quite interesting to us, because we know from the Acheulean onwards, this is the sort of before now, this is the start of when people were imposing things like symmetry and certain shapes, this teardrop shape. The starting cobble that ends up being a hand axe doesn't, those two things don't look the same. People are actually making the shape that they want. And so here at Ubeidiya, in the very start of the Acheulean, or maybe a developed older one, we have another example of this same thing. Humans actually imposing this shape, and not just a sphere, but also symmetry. Like a hand axe is symmetrical in a few axes. Spheres are they're entirely symmetrical. And so if we can find this similar reduction sequence with the similar goal of making a sphere in, for instance, the spheroids that belong at the end of the older one or developed older one, then we have even earlier evidence of humans actually imposing geometric constraints on stone, imposing things like symmetry. But this is, questions for future work. But that's my talk for today. Thank you very much. thank you also to all of these people, without which this would have been impossible. So, thank you.